All right, so let's talk in detail about series circuits. Series circuits are going to be completed paths where there's only one option for our electrons to move. So it says one pathway because the wires are going to be connected so that all of the electrons move through all of the parts of the wire. The voltage is shared between the resistors. If one element or device goes out, then the entire circuit is not going to work. All right, so let's pause for a moment and talk about what exactly that means. Here you can see that I have a battery connected to a wire with 3 light bulbs, and there is a switch. So right now this switch is open, so there's no electricity flowing. My light bulbs are going to be turned off right now. They don't tell us what our positive and negative end of this battery, where those are located, so I'll just kind of pick one and we'll go with it. For your diagrams in the future, you will be able to identify positive and negative by the length of those lines on that battery symbol, okay? So let's go ahead and close this switch so that the circuit is now complete. And when we do that, that's going to cause the electrons to flow out of the battery. They're going to move through the wire, and they're going to make their way through all of these light bulbs and then back to the battery, okay? Now, when we say if one element goes out, the whole circuit doesn't work, let's understand what happens. If this middle bulb breaks on us, let's say that we have a filament here and it just kind of burns out, all right? If that filament burns out, what that means is that the electrons are no longer able to pass through that light bulb and exit to the other side. So for our circuit, this entire path is gone, which means that the electrons do not have a complete path. And remember, either all of the electrons are moving or none of them move. So the moment that this filament burns out, we create a gap in our circuit. So when this goes out, the whole circuit turns off because all of the electrons have stopped moving. The more bulbs that we add to our circuit, the dimmer each of those bulbs is going to shine. So we're going to go back to our simulation, and I'm going to show you what that looks like. So we'll go ahead and just make this a regular wire because I don't need the switch right now. So you can see that I have one bulb on my circuit, and it's shining pretty bright. And I'm just going to bring lots of other bulbs over and add them to our circuit so that we can see how the addition of the other bulbs changes the lighting. So in this simulator, you can see that the brightness of the bulbs have decreased. Remember, the simulation is also set up to show us the conventional flow for our electric current. So you may have noticed that we had those arrows showing that current flowing real nice and clear in the beginning, but right now there are fewer of them, or they're spaced farther apart, really is what's happening. So that's there to illustrate that they are moving slower. We'll talk about why that is later on in a moment. But you can also see that the image is a little faint, and I think they're just trying to visually represent to you that the more light bulbs that I have put on the circuit, the lesser our current. It has slowed down our current. Now I'm going to take each of these light bulbs and replace them with a wire. So look at how dim these light bulbs are, and as I begin to eliminate them, you will see, number one, my electrons are now more visibly present. They are moving faster, and my light bulb has now changed to show that it is shining brighter. Okay, so that's what we mean when we say more bulbs are going to be less bright for our bulbs. All right, so let's talk a little bit about this statement of voltages shared between resistors in a little bit more detail, along with addressing some other vocabulary that we need to know about our circuits. So it says here that current is constant throughout and voltage is shared between the resistors. So I want to make sure that you have remembered the vocabulary correctly, and I want you to understand how those vocabulary words actually physically apply to our circuit. So first, I want to pause and look at the illustration and point out that we have two batteries on this particular circuit. You can see that I have that battery symbol twice. Each of them has a labeling of 6 volts. So for this particular circuit, we have a voltage collectively here of 12 volts for the whole circuit, okay? Now, our electrons are going to exit the positive end of the battery, and they're going to move through the wire, returning to the negative end of the battery. So when we say that current is constant, what we mean is that these electrons are going to pass through all parts of the circuit. So if I ask you a question about the current at any given location, the answer is going to be the same at all the locations because they all experience the same flowing electrons. Remember, those electrons all move together, okay? Either they're all moving or they're not. None of them are moving. So when we say current is constant throughout, it's because the current is going to flow the same everywhere. Remember, I represents current, and we said that this was the rate of flow of electrons. So it's the rate of our electron flow. And we measure current in amps. And when we think about the meaning, the rate of electron flow, we're going to have some electrical charge in coulombs divided by some amount of time in seconds. So our amp means coulombs per second, okay? So it's a rate, so that means we're always dividing by time. So that's what our amps represent, coulombs per second. We often say fast or slow as kind of a description here for that movement. Now the next statement says that voltage is shared between the resistors. This is a very important basic concept that I want to make sure you guys fully grasp. So I'm going to give you some details as to how the voltage is going to change as the electrons move through this current. So we have our 12 volt total, 12 volts available from our voltage source. Our two batteries are going to combine to give 12 volts to our electrons. Now remember, voltage represents the amount of energy available per coulomb, okay? So V for voltage, and this is our ratio of energy per coulomb. And remember, a coulomb is a bundle of electric charges. So voltage is measured in volts, and based off of the definition, this is going to be how much energy in joules divided by how much electrical charge in coulombs. So joules per coulomb is our meaning, or a way to interpret what the value of a volt represents. So for this particular situation, I have 12 volts in my circuit. So as the electrons leave, they are carrying 12 volts of energy. Now in a previous lesson, we had a little illustration of what looked like little men carrying buckets of energy, and I said that those men basically represented our bundles of charge. That's our coulombs, our electrons coming out of the battery, and the liquid in their cups represents the energy, right? So they're all going to come out of that battery with all 12 volts of energy. Now, when they get to this first device, that device is going to need energy in order for it to work, right? So my electrons are going to take some of the energy that they are carrying, and they are going to dump it into whatever this resistor is. Now, how much voltage is that device going to receive? There's not a set rule for you to know what that number is. You have to actually calculate that, and we'll do a calculation later so that you can see how that will work. For right now, what I want you to understand is the device determines how much voltage it receives, all right? So just because there's 3 devices doesn't mean anything about how much voltage each device gets. You have to do the math for them individually to know what that value is. I'm going to just make up a number so that we can get the idea across as to what is happening with our voltage. So let's say that this very first device requires 8 volts of energy, or 8 volts, sorry, in order for it to work. My electrons are going to pour some of their energy into this device. So now when they leave whatever this resistor is, they are no longer going to have completely full cups of energy. So that ratio of energy per coulomb has now decreased. So as those electrons come out of the device, they do still have voltage available, but the amount of voltage has changed. They now have less voltage than what they started with. So according to our hypothetical situation here, if they started with 12 and they gave 8 volts away, they have 4 volts remaining. So when our electrons reach the second device, this device is also going to require energy. So our electrons are going to pour some of that voltage into the second device. So let's say that this device receives 2 volts. My electrons had 12, lost 8 of them. They were left with 4. Now they gave away 2, so now they're left with only 2 volts in their cups, 2 volts available. So these electrons are going to exit that second device with even less voltage than they had available in the beginning. When they get to whatever this third device is, this third device also needs the electrons to dump some of its energy into that device so that it can run as well. And so this particular device ends up receiving 2 volts. Now, how did I know it was 2 volts? Again, I'm making up numbers hypothetically so that we can just kind of get the main idea across. There are some conceptual things though that we can apply here. These 2 devices had exactly the same resistance, so even when we do the math, they would require the same amount of voltage. But the other more important main idea I want you to grasp right now is if we had 12, we used 8, that left us with 4. We used 2, that left us with 2. We used 2. What are we left with now? We are left with 0. Now, this is a super important main idea. Our electrons will always give up all of their voltage as they move through the circuit, and they will always return back to the battery with 0 volts left. Exit with all 12, return with 0 every single time. It does not matter how many devices are on the circuit. It will always start with however much voltage is available from our voltage source and return with none, okay? If I asked you for the total resistance that the electrons experienced as they were moving through this circuit, we would simply take all of the resistance values and add them up, and that would give us our total. All right, at this time we are going to work through one example circuit. So you can see that I have a circuit with 3 resistors. This particular circuit has 2 batteries. Not all circuits will have 2. You could have 1, you could have 5, you could have 3. This drawing just happens to have 2 of them. So let's start off by looking at our voltage source, and we are going to recognize that both of these batteries are going to contribute voltage to the circuit. So collectively, I have 12 volts available for my circuit. So one of the values that it's asking me for is my total voltage. So that's going to be 12 volts. Now, I'm going to go ahead and calculate our total resistance. So we established that we are going to calculate the total resistance in a series circuit by simply taking our resistance values and adding them all up. So it's simply the sum of our resistors. So my total resistance is going to be the first resistor value, which is 1, plus the second resistor value, which is 2, plus the third resistor value, which is 1, which gives me 4. So I have 4 ohms of resistance in total that my electrons experience as they move through the circuit. Now, how did we know which one is supposed to be number 1, number 2, and so forth? Remember that our electrons are going to move out of the positive end and return to the negative end. So as my electrons move through the circuit, they are going to encounter this resistor at the top of the diagram first. So that becomes number 1, and then we just kind of number them from there. So moving forward, that's how you should know what R1, R2, and so forth are going to be on whatever diagram you're using for the question. All right, next they are asking us for the total current. So we're simply going to use Ohm's law in order to come up with this value. So Ohm's law is V equals IR. If they are asking me for the total current, I am going to calculate my total current using the total voltage and the total resistance. Make sure you're using all total values together in this formula. So I have 12 volts total. I'm looking for my current. My resistance is 4. So we're going to divide by 4. So 3. So my total current here is 3 amps. Now, it's asking me for the voltage over R1, the voltage over R2. So I want to pause and make sure you guys understand what that means and kind of expose you to some other ways that we may go about asking for the voltage. When we talk about voltage, remember it's that ratio of energy available per bundle of coulombs or per bundle of charge. So our voltage is going to be how much voltage is used by the device. So when it says V over R1, we could also say the voltage drop from R1. Why would we use the phrase voltage drop? Well, as I demonstrated in the notes earlier, the amount of voltage available is going to decrease because the resistor is going to take some of that voltage away, so the value drops, right? We may just tell you V1 equals question mark, and we're just asking for the voltage at that first resistor, or we may say voltage at, and then give you resistor 1, 2, 3, or whatever. I want you to know that all of these are representing the same thing, and you are going to be calculating how much voltage was used by whatever device is at the location in question. So voltage used by that resistor, whatever that resistor is. Okay, so let's go ahead and calculate our voltage. We have V equals IR as the formula to use. If they are asking me for the voltage over resistor 1, that means I am going to calculate voltage at location 1. I'm going to put the current that goes through the first resistor and the value of the resistance from that first resistor. So V1 is equal to. Now, how am I supposed to know what my current value is? Remember, we discussed in the basic notes that the current is the same throughout. The electrons are going to travel through all of the parts of our circuit. So that very first resistor is going to experience the same current as all of the other resistors. So when we said that our total resistance was 3 amps, that means that the value of our total current is 3 amps. So that means that the value of the current going through the first device is 3 amps. So 3 times, and then the resistor value just comes from the illustration. 1 is 3. So V1 is going to be 3 volts. If I want to calculate the voltage across resistor 2, you know what, I will put this over here. If I'm going to calculate the voltage across resistor 2, then I'm going to use current through device 2, resistance from device 2. So this is going to give me 3, because it's the same everywhere, times 2 at this location, so 6 volts through that second resistor. All right, now, how can I maybe check what main idea could help me to spot if I've made a mistake here? Well, remember we talked about the voltage is going to be used by the time the electrons run all the way through the circuit. So if we were to take our voltage, and let's think about what our electrons did. Our electrons moved through the first resistor, and they gave away 3 volts to the first resistor, and then they gave away 6 volts to the second resistor. And although this question didn't ask me for the voltage used by the third resistor, I could do the math and see that it comes out to be exactly the same as R1 because they have the same resistance values. So it's going to give away 3 to the third resistor. So how much voltage did the electrons give away after they've gone through all 3 of these? They gave away 12 volts. That looks familiar. Wait a minute, we have 12 volts total for this circuit. So if you wanted to check yourself, you could add up the voltages that you calculated and they should equal the battery. This is also another way for you to calculate your total voltage. You just simply add up the voltage values for whichever devices you have in your circuit. So I just wanted to show you that as number 1, kind of a way to check yourself. Number 2, it's another option for calculating your total voltage, and I would suggest that you use whichever is most convenient based off of the information you have.